So, hi to everyone. As Fabian said, I am working for ERNW. I've been doing this for over 4 years now as incident responder, incident analyst, and I studied computer forensics. And this talk is basically about my master thesis. It's about Ceph, software-defined storage. We will talk about this a little later in some slides. Yeah, my master thesis is already quite old, so I wrote it about 5 years ago at FAU Erlangen, and I looked at software-defined storage, so Ceph is software-defined storage, to get an idea what you can see on disks that were used in a cluster, Ceph is used in different setups, like, for example, in OpenStack you can find it quite often, and there are a lot of other use cases. Ceph basically works like this. You have something called OSDs, which are hard drives that are used by Ceph, and those can be normal spinning drives, or those can be SSDs or NVMEs, doesn't matter. And you join all those OSDs that are in your cluster of computers together to something called Rados. It's like an object storage, and all the data you want to store there are dropped in form of objects. So you have a flat hierarchy in there, and all the data is accessible in some way as object. On top of that, you have different kinds of accesses that you can use. You can use something called CephFS. This is basically that on a client you mount a POSIX-compatible file system, and there you can interact like via a normal file system. You can create directories, you can create files, you can delete them, you can move them, and stuff like this. And you can also use something called RBD, Rados Block Device. This is that the client sees a block device, and you can use it as a normal block device on your computer, like something /dev SDA or SDB or something, and you can simply create a file system in this block device, or you can do anything else that you can do with a block device in Linux, for example. And there are different other APIs that you can use, for example, Rados Gateway, where you also can use like REST-based communication to drop data or to read data. But I focused mainly on CephFS and RBD. Because they are quite interesting from the metadata perspective to get an idea how you can, for example, reconstruct a block device or parts of the block device depending on how many drives you have from a cluster. The background also was that Ceph changed the underlying implementation, how data is actually organized on the drives in 2017. Before that, they used XFS, and they dropped all the data in form of files in there. And they implemented something new called BlueStore, and I wanted to understand how it works. And because nobody else did it before me, I had a lot of work for my master thesis there. I categorized all the data that I found based on the categories introduced by Brian Carrier. He is quite famous for doing work in the file system forensics area, and he introduced 5 categories called file system category, content, metadata, file name, and application category. So the file system category is basically all the data that describes the file system. So that it says this file system is, for example, an NTFS, or this is an ext4. and it has a certain size, it has certain different other attributes, and like this metadata for the file system belongs to the file system category. You also have the content category, which is, yeah, as the name says, the content of the actual data. If you think about a normal file system, it's like the file content that you write to the drive, or also the contents of directories. And it also includes like the metadata that tracks if certain areas of your file system are in use or are not in use. The metadata category is also straightforward. It contains the metadata of files, for example, timestamps, access permissions, owners, something like this. The file name category is also straightforward. It includes the file name and maps it to a file system internal ID. For example, if you know something about ext and related file systems, you maybe know inodes, and here you have IDs, and you map it to the actual file name or directory name. And at last, there is the application category. This is used for additional stuff that you want to do with the file system. For example, you want to track quota information, or you want to have a journal, and this is included in the application category. So I looked at all the data I found on OSD drives and tried to categorize it so that other people that want to analyze OSDs know where and what they can find in these categories. I also implemented a little tool called Vampire, which is a Python program which can do all the analysis I implemented. I did not implement everything you could, because that's a lot. But so the basic stuff is working, and it's open source. And if somebody's interested, you can improve it. So one limiting factor is, of course, that not every OSD stores every data or every object or every data that is stored in the object storage, because you have a cluster of different systems. You usually have a certain replication factor. So, for example, each object is stored 3 times or so, depending on your configuration, somewhere in the cluster. And this means then that it's stored on 3 different OSDs, but usually you have much more OSDs, much more storage devices, and this means that you will, on every OSD, only find a certain subset of the data that is stored in the cluster. And where an object is stored is determined by the Crush algorithm. It is deterministic, so if you know the name of an object, you can compute where it should be stored. But like, it seems to be random, so that the data is actually distributed quite evenly throughout the whole cluster. So this means if you have objects with a very similar name, they're usually not stored on the same OSD, but it appears to be random where it is stored. And as I said before, Ceph changed the implementation or how the data is stored on the OSDs. Before BlueStore, there was something called FileStore. There they used on every OSD an XFS file system, and each object that was stored in this OSD was basically just a file in there. And for metadata tracking and storage, they used key value store implemented as a level DB, like it's a database, and they experienced some performance issues with that, because like how they manage the data and how XFS managed the data led to bottlenecks in the performance with the journal of XFS, for example. So they implemented something called BlueStore, where the daemon, the Ceph daemon, manages the whole OSD by itself, and there is no real file system on there. There is a little file system. It's very basic. It cannot do much. It's called BlueFS. For example, you can just create first-level directories, but you cannot create subdirectories in this file system. And the only purpose of this file system is to store the RocksDB, which is the key value store that tracks the metadata, because they didn't want to implement it on their own somehow on the raw device. But the rest of the data, like the objects, the actual content, is managed by the Ceph daemon on the OSD without intermediate file system. Yeah, so that's for the theory. And now some more theory. What did I do? I created a setup of 3 virtual machines with some small OSDs in there, just 3 VMs and 3 OSDs in total, so that it was easy for me to keep track of everything. And I created like different states of the Ceph cluster. At first I had an empty Ceph cluster and created snapshots of the file systems or the drives. I then configured it, then I created data in there, and so I knew all the time what I should find on the system and could match it to what I actually found. I also had access to data from SAP HANA installations on Ceph clusters that I could use to validate my implementation, to see that it works with large amounts of data and with certain edge cases. And of course, I read a lot of source code. Because it's open source, it was quite easy to get the source code. And I also read a lot of hex dumps, like just plain data from the drives. And this is how the basic structure of an OSD looks like. In the beginning, you have a BlueStore superblock, which contains all the basic information. Like this is a BlueStore OSD, for example, and it belongs to that Ceph cluster. You have then a BlueFS superblock, which points to this very simple file system, the BlueFS. And you have an OSD superblock. And this contains some more information about how the OSD is configured and what you or where you can find stuff. And then you have the most part or the largest part of the drive used to store the actual Ceph objects. But in between, you have different areas where BlueFS is stored. So you have different allocated areas that can be only one, that can be fragmented across the whole drive. And at some points, you find the area for BlueFS. And how we can get the content correctly, I will show later. Yeah. And the BlueFS, as I said, is used to store the key value store. It contains all the metadata of objects, like when was the object created, like the context if the object belongs to a CephFS or an RBD. And I wanted to restore the key value store, obviously for metadata analysis and to find out where the object content is actually stored. And so the first thing I did was to re-implement the BlueFS access and to be able to get all the files from there and to analyze it. So BlueFS, as I said, stores the key value store. We can find out about the structure and the content of the BlueFS by reading the BlueFS superblock in the beginning. It contains a pointer to the first part of, or the first allocated area of the BlueFS. It also contains the information where I have to start reading something called the transaction log. And the transaction log is basically a journal which contains entries for every action that happens on the file system. So if you create a file, it gets an entry to the transaction log. If you rename a file, if you move a file, if the file gets larger, and stuff like this, and each of the operations actually gets a new entry in the transaction log. And because space in the first allocated area is limited for the transaction log, at some point in time you will have in the transaction log a transaction which says that the transaction log was increased and where to find the next part of the transaction log. So you have to read from the start each transaction to find then all the rests of the transaction log, each allocated area of BlueFS, and then at the end, when you found the last transaction, you know the current state of BlueFS. And then you can extract the data for each file, because then you know which extents are used or what areas of the disk are used by each file and what's the size of a certain file. The transaction log also could be shown like this. It contains, as I said, transaction, but in each transaction you can have different operations. Operations can be, for example, file created, file renamed, stuff like this, and a transaction combines several operations that happened at basically the same time. So what I then did, I implemented this interpretation of the transaction log, and so I was able to get the key value store. I started by reading the BlueFS superblock, jumped to the transaction log, read and interpreted all the transactions sequentially, had a list of files then that I could write to my analysis machine, and then I used the only external dependency for my little Python program. It's called LDB. LDB is a program like a debugging tool for RocksDB. By the way, RocksDB is a key value store implemented by Facebook. Like, it's a project by them, but it's also open source. So you have to build it on your own, and then you can dump all the data that is contained in the key value store. Yeah, and because now when I dump all the data from the key value store, I have the object metadata. I can now look at what do I see there. I see a lot of entries where the key starts with different letters. So if you, for example, look at all the keys starting with S, then you know the value of this key will contain OSD metadata. If you look at something that starts with O, an uppercase O, it will contain object metadata. Or if you look at a key that starts with lowercase b, it will contain in the value a bitmap for a certain part of the drive that will tell you if certain blocks are in use or not in use. And to interpret the bitmaps correctly, you have to read the keys or the key values that start with uppercase B and interpret the data in there correctly. But the most important part here is, or the most important entries are the ones that start with O and M, because they contain object metadata and some additional object metadata that are then necessary to interpret the data, for example, for Cephfs, to understand if an object in Cephfs is a directory or a file, and what's the parent directory of a file, and stuff like this. And to understand how those different metadata entries work together, I have this handy chart. So you look at for example, a key that starts with uppercase O. Then we have behind that the name of the object. Afterwards, there's a lowercase o. Then you know this is the value of this entry contains like the basic information for this object. It contains a data structure that is called onode. In there you find an OID, which is an internal ID for this object, but it's different from the name of the object. You find the size of the object, some additional attributes, extended attributes, some flags and stuff like this. And you find the beginning of the extend map. And this extend map just shows you like where on the drive you can find the content of the object. And if the space in this value in the key value store is not sufficient to store all the data, then you have like these entries that end with an X. Like you have then uppercase O, the name of the object, lowercase o, then an ID, like a counter for all the additional objects, and then lowercase x. And in there you find more extend map entries, and you have to combine them to be able to restore the full content of the object. And when you then have the object ID from the O value, you can go and look at the M entries, because if you look at M followed by the object ID, you will find different entries that are followed by a certain type, like there are different types, and you have to read source code to be able to find out what types there are. And then you have in the value some encoded data structure depending on the type, and then you find, for example, what is the what's the content of the directory in Cephfs, because that is stored in such a metadata entry. So that was quite a hassle to implement and to understand what's going on, but at some point I figured it out, and then I could look at how this RBD and how this the Cephfs work. So looking at first at the easier part is looking at RBDs, because you can configure a lot of RBDs in your Ceph storage, like for each client or so that you have there. You can create block devices that are then provided to your clients. Because of that, you have a unique ID so that you can store different RBDs next to each other. And then the object names will be like RBD data followed by the ID. And then you find a block ID in the name. And the block ID is just something like the sector counter. So the first sector of your RBD is stored in the block with the counter 0, the second in the one with the counter 1, and so on. And then when you read the data from an OSD, you can look for all the RBD data objects followed by a certain ID. And you can order these objects by the block ID and reconstruct the data from the RBD. But of course, only the part that is stored on your OSD that you have available for analysis. Important is also that it's lazily allocated. That means if you create the RBD and you don't touch it, there will be no object, even if the RBD in theory is 100 gigabytes of size. So you never know, if I don't find a certain block, if it was never created or if you just don't see the object because it's stored on another OSD. And of course, when you touch the RBDs by creating a file system in there, or you write data to there, then the different objects are created depending on the sector where you write the data in the RBD. You also have another object, like the RBD header object followed by the ID. It contains metadata like the creation time, some features, if it is locked, for example, because a client is currently using it. And that's quite nice because you find out the creation of a block device. Usually in a normal setup, like when you just look at a hard drive, you don't know when there was something created like the block device. And there you can see it in a Ceph cluster. Yeah. Another thing is CephFS that I looked at. And it's not to be confused with BlueFS. CephFS, yeah, as I said, is this file system that can be used and mounted by clients, just as the normal file system. You have directories in there, you have files in there. And important is that you don't have a one-to-one mapping between file and object. So if you create a file that is quite large, you will end up with a lot of objects in this in the RADOS, because the mapping is that you create a file. The file gets assigned an inode ID, and then if you have inside your cluster a maximum size for objects, which is, let's say, 4 megabytes. But if you have a file that is 20 megabytes, you will end up with 5 objects for the inode 1000, for example. Yeah. So when you want to reconstruct a file, you have to find all the objects that belong to that inode of your file. And of course, you have to be lucky to have all the OSDs that contain all the chunks of the file. And then you can join those chunks together to the original file. Yeah. Then how we can get the path of a file, that's quite easy. We have an extended attribute as the parent extended attribute. And in there you find a list of inodes that are the parent directories of that file. Yeah, and when we have a directory, for example, we can look at this at a certain metadata row in the key value store of type dash, and we will find metadata for the directory. And when we look in such a for such an object at the at an M row that contains a file name followed by _head, you will find some metadata for the file that is not stored at the object that represents the file, but it's stored there in the directory metadata. So there you can find permissions, for example. And then we have some more objects that store interesting data, but I didn't have time to look at those things deeply. There's, for example, the object with ID 600. It contains the file system journal for CephFS. Yeah, and during my master thesis, I figured most of the stuff out, how it works, and then I created my tool to be able to analyze the OSDs, and I created, or I named the tool Vampire after Vampirotoitis infernalis, which is this squid here in the lower corner. This is because Ceph stands for cephalopod, and this are squids, basically. It uses Python 3, and it doesn't use any Ceph libraries because I didn't want to be relying on some libraries that might not show all the available information to me. So I implemented everything on my own to be able to parse all the data structures. And now Vampire can show the data of the file system category, and this is, for example, when was that OSD or the CephFS, or when was it created? I can reconstruct and extract data from the BlueFS and load the key value store, and I'm able to interpret most of the metadata that is stored in the key value store. I can decode something that is called OSD map. OSD maps contain topology information about the cluster. So even if I don't have all the OSDs of a Ceph cluster, I am able to tell you how many OSDs were configured in the cluster. And if at a certain point in time an OSD went down or came up again. So it's possible, for example, to tell if there was a downtime of a server in the cluster. And not only can I find it by looking at the metadata, but it's, my tool is also able to carve for this data. That means just looking at the plain data inside the drive and to find like the start of an OSD map to be able to interpret it. And of course, I can decode object metadata, and then based on that, I can extract the actual content of an object. Yeah, and because, as I said, the data is often split of a file, for example, or of an RBD, is often split across different objects. My tool is also able to reconstruct the different objects to the actual file that they represent or the RBD that they represent. And yeah, and if you have more than just one OSD available, it's able to reconstruct like the data of more than one OSD and join it accordingly. Yeah, and for CephFS, I can reconstruct file names and directory names. Here it's quite interesting, even if you don't see the objects that represent a certain directory, you're still able to tell, in some cases, that a directory exists or existed in CephFS, because maybe you find an object that represents a file, then this file metadata contains like the names of the parent directories, and so you are able to tell that there should be somewhere a directory called ERNW, but you just don't see the content, but you know that you see a file that was stored in that directory. Yeah, and also I can, with my tool, extract slack spaces. This is, for example, the file system slack space, which is like after the end of the file system or the OSD up until the end of the actual drive. Or, for example, for objects, if an object is 4,000 bytes of size and like your allocation unit size is 4K, then you have 96 bytes that are not overwritten when the object is created. So in the slack space of 96 bytes, you maybe find data of a previous file. I can also determine the unallocated areas of an OSD, and you can use that to find in this unallocated area the content of objects that were stored there before and were just marked as not in use anymore. Yeah. And for statistics, it can also look at each sector, like or 512 kilobyte block, no, byte block, to determine if the sector is completely unused because it's zeroed out, or if there is some data in there that is just marked as unused. No. And as I said, my training data was taken from my test setup and a database system based on SAP HANA. I used my tool to analyze everything. I looked a little at the performance. I checked that I found files that I should find and stuff like this. It's all included in my repository where I published the tool so that yeah, everybody can test that it works and can test the tool actually. And before I go to the demo, I have the conclusion at Outlook. Yeah, so what I did was I documented the data structures, categorized the data, I implemented a tool that makes use of everything I found out, and yeah, but still it's lacking some certain stuff. For example, I just looked at a certain type of setup of BlueStore, where the key value store or the RocksDB key value store is stored on a single drive, but you can have, for performance reasons, some slightly different setup where you put some parts of the key value store onto another drive that is quicker, for example, to have the database journal on there or the write-ahead log. And what I also did not look at deeply is the Ceph journal. For this reason, it's possible that I missed the existence of files that were written or created or changed just before the OSD was turned off. I also didn't look at things like Rados Gateway or librados, which are other ways of access to the Ceph cluster. Then you can also have compression in your cluster and also encryption. I didn't look at that. And also had some problems to verify checksums. I still don't know why, but I never could compute the correct checksums for the data I found. And the checksums are always stored next to the data, so yeah, it should be possible to, but I didn't figure out how to do it correctly. And then something that is now very new is that Ceph started working on something called CStore, which will eventually replace BlueStore. Because they figured out that BlueStore is still not performant enough and has problems with using concurrency. You just cannot have multiple threads in BlueStore to access the drives, and they want to make it more parallel, and for that they need CStore. And this would be then something for another master thesis, for example, that somebody figures out how the data on such an OSD would work. Yeah, and now I have still some time, and I can show you just quickly what the tool looks like. And yeah, the first thing is that I show you what a listing of objects looks like. No, we start with the file system metadata. I didn't use the tool in quite some time, so I have to use the help page. And if we use the BlueStore label flag, we see, for example, when the BlueStore was initially created with the OSD meta information. So you see that it was some time ago. You see the size of about 100 gigabyte, and you see some additional metadata, like there should be a RocksDB database as key value store. There you see that there is some versioning. So this is like version 26 of the OSD data and other things as well. And you see, for example, here's something called whoami0. This means this was the first OSD drive in the cluster that was configured. If you look at other OSD images, you will see that there is, then the ID is 1, 2, 3, and so on. And so if you find something with whoami100, you know that there were at least 100 drives in the cluster. And then there's also some information where you can look at the slack space of this file system or this OSD data, so to figure out if after the OSD data you find some additional data on your image. And there are also some other information. Then you can look at the BlueFS superblock, and there you find the information about this very simple file system where the RocksDB database is stored. You find like the size, where or how many extents or how many areas how many areas are there on the drive allocated for BlueFS. And then you find here information about the transaction log, the size of the transaction log, where the content of the transaction log is stored on the drive, and then you find a list of files in this file system with all kinds of metadata displayed here. And when you have this, you can just use the ls object or objects flag. No, you can use the ls objects flag, and here you get now a list of all the objects stored on this OSD. So you see there are a lot of objects that have names like starting with a number. Those are all the files and directories stored in the Cephfs that is configured in there. The object with the name 1 and then followed by like a counter, like those contain the content of the root directory of the file system, and everything like starting with this number that I don't know what number it is, those contain the actual contents of the directories and files in that file system. And you see, for example, here, the file with this inode that ends with 15, it contains consists of several chunks stored in 5 different objects on the drive, and you have to join those 5 objects together to get the full view of the file content. And when we jump to the end of the list here, we see some more stuff like OSD map objects. Those are the ones that contain like the topology information about the cluster. You see also that there is something called MDS snap table. MDS is the metadata service that is used for Cephfs. If you're interested in how it exactly works, you have to read a little about Ceph, because I don't have so much time here to talk about all that. And here at the end, you see, for example, RBD data. So we have a RBD with an ID that starts with 23 and then something more. And it has at least 11 objects. So we see the first 11 objects that belong to that RBD, so the first 11 sectors of this block device. But we don't know exactly if it's everything of that RBD that we see or if there's more content in theory, but we just don't have the OSDs that contain the rest of the RBD. To figure this out, we can have a look at like more RBD metadata objects that then contain, for example, the size of an RBD. And then we would figure out that the RBD is, for example, 10 gigabytes of size, but we only see some kilobytes, and then we can assume that we don't see the full size of this RBD. Yeah. And when we did this, we can also use the help page again to extract all the data and all the objects that I find to a directory. It takes some time. And afterwards, in the directory extract, we find all the objects, like organized in directories, and I can go, for example, to the directory with the name 1. It contains the root directory information of the CephFS. My tool creates some symlinks to the children or all the subdirectories and all the files in that directory. So I can go to the test files directory. In here, I see that there are, for example, some images, or a directory called images, probably. And so I can go through the content of the whole CephFS in here. Of course, I could reconstruct it in some other way. And if I find here, if I look here, I see that there are actually files called, or from the name, I would assume they are JPEGs, so pictures actually. And I could go to there. And in here, I see that it created something called self underscore and then the name of the file. And now I can check if my tool worked. No. Probably I didn't reconstruct it correctly before, but in theory it... no. I opened the wrong file. I have to open this here, and now it should work. And I have a file that was stored as an object somewhere on the drive. And I have to say this is quite a simple example because this file is just stored as one object, but with a larger file, I have to reconstruct, like put all these object files together. It's just a simple, like a cat, for all the files together into one file, and then you can open it as well. So, yeah. You can ask now questions.
All right, are there any questions in the audience? Yeah.
Thank you for the presentation, very interesting. Who are the main users of Ceph? Which type of environments is it used primarily? Yes.
So on one slide I had an example like OpenStack. In certain setups in OpenStack stores VM images, I think, in Ceph. This is, for example, a huge use case where it's often used. Then, for example, as I said, I had access to training or test data from SAP HANA databases. So there are offerings, for example, for SAP HANA that store data in such Ceph clusters. And there are a lot of setups also in cloud and cloud-native environments. Okay. But also some interesting people do it at home and to save their, I don't know, their photograph collection and stuff like this.
Thanks.
Yeah.
All right, any other questions? Maybe I have another question. So with Ceph, is there any possibility to have something like a disk encryption that is implemented in Ceph and then basically your tools wouldn't work, or is the encryption key also somewhere saved and you can recover that?
I didn't cover encryption. I know that it's possible. What I didn't mention here, to make it a little more easy, is that all the Ceph OSDs are like wrapped in LVM. And I think that it's then somehow implemented via encryption in LVM, but I'm not quite sure how it works. I didn't look at that. And of course, if something is encrypted and we don't find the key, we cannot decrypt it, except it's somehow flawed. But this is, I assume, not the case. But somebody could test that.
All right, then. There's a question.
Could you maybe explain what would be the use case for your tool in particular?
Yeah, it could be, for example, that you want to recover data from a cluster that is somehow broken. That would be a possibility. But also, like, you find somewhere a drive and you want to find out what data was stored in there because some employee smuggled it out of a data center and sold it on eBay or so, and you find it and you want to understand what data was actually affected. So this would be, for example, a use case.
All right, then do you have any other questions? Otherwise, I would say we thank the speaker again. Yeah, thank you.